Hello, my name is Sami Alhasan. I'll be talking about critical raw materials selection for this research paper. The title of the paper is Material Selection at Critical Raw Material Perspective. The authors are Paulo Ferreira and Franco Bonallo. The specific scope of study is going to be raw materials criticality in this case, and the key question addressed here is how does raw material criticality affect the way we choose a material for a certain type of application. For the methodology, the model used is going to be critical raw materials, in short CRMs. For the CRM processes, we have the processes listed here. Basically, they are indexes that are rated from 1 to 5, 1 being least critical and 5 is being more critical materials. And the methods for determining which critical material is needed is the definition of the design requirements, constraints, objectives, or free variables, screening using constraints, ranking using the objective, seeking important information. On the top right, here we have a list of all the critical materials considered by the European economy. However, in this Ashby chart, we are not going to be using all of these materials. So for the key result from study, the first one is going to be how does raw material criticality affect material selection for a bicycle fork? So bicycle fork is the green part here shown in figure 3, which is basically what's holding most of the front part of the bicycle, which is connected to the frame and the front wheel. And in table 4, you have the materials that are suitable for making a bicycle. In this case, with criticality, the main thing to focus on here is CI sub A, which is criticality index, and criticality index is basically the overall criticality value per unit mass of alloy, and so the lower that value is, the higher the material index is going to be. It's also shown here in this equation 19 from the research paper. In this case, titanium has the highest material index, so titanium would be the best material for this application. And on the right, figure 5, you have the Ashby chart and the material index line, and the suitable and the other suitable alloys that you could use. For key result from study, the second key result from study is going to be how does raw material criticality affect selecting a connecting rod for high performance engines? So basically, a connecting rod is going through a lot of pressure, stress, and it is important for a connecting rod to have a high fatigue life. So in this case, we have titanium, beryllium, aluminum, and magnesium. And so in the Ashby chart, we have more materials, but in the tables here shown, these were the most used materials for making a connecting rod. And actually, not if we're selecting the best material for a connecting rod for a high performance vehicle or for a high performance engine, just focusing on performance, beryllium would be the winner in this case, but in this case, criticality put into perspective here, titanium would be the best, since again it has the lowest value of CI sub A, criticality index. And so titanium would be the best choice for this application. And minimum M&M star values will represent the best material choice in terms of performance and reduced criticality, respectively. For a summary, with CRM selection, which is actually developed by Ashby, and the CI sub A, which is again the overall criticality value per unit mass of alloy method, material index M star is obtained, and is a very useful. When those are obtained, it's very useful to have them for selecting the desired material for the application needed. And overall, going through this research paper and studying it, the quality of the information is really good in my opinion, even though everything was kind of all over the place in terms of having explanations on a page, and then the figures for the applications are always at least a page ahead or 2 pages ahead, so it wasn't the easiest to read, but it was bearable. And most of the information and data used personally is very useful for my career.